Okay, I'm going to record this webinar as well for the ones who could not attend. All right. So if everyone can see the screen, I think we can get started. The recording is on, right? Perfect. All right, so this I wanted to make a webinar about applications for shortwave infrared. As you may know, some of you already sold some of our cameras, so you already had some ideas about applications, but the idea is to broaden the range of ideas so that you can hopefully better assess the market and sell to different kind of customers. So I tried to focus on the volume cameras that we have. These are written at the bottom, C-RED 2, ER, Light, and 3. But sometimes you will see that it also fits to the high-end cameras, C-RED 1, C-RED New Space, as an example. So right, I think we are almost all here, so I can go back. Yeah. So I was just starting with the presentation. Of course, if you need help or if you have any questions, I will let you ask questions at the end. We will have about 10 to 15 minutes, but my email is also written at the bottom. So yeah, as the title says, it will be 10 key applications. Some of them are already known. For example, adaptive optics. This is something that we already know very extensively, and this is where most of our cameras go to. But there are also other applications that you may also know. I will not list all of them, but these are the 10 applications we will talk about. Of course, this is a small disclaimer. This is based on my own research and with the help of the other product managers, but obviously it does not prevent us from listening to the customers because some applications may be very niche or very specific. So this is just a general statement. So the first application, you will see the scheme is quite the same for all the applications. I will start with a small introduction. I will show you some key examples, customers that we already have, and I will show also a list of specific feature of the camera that fits very well to the application. So adaptive optics is the first one. Some key terms that may be useful during discussions. And here, this is most of our cameras. So here I only talk about shortwave infrared, but of course we have also the CB2 in the visible range that would fit in this category. So yeah, adaptive optics, for those who may not know, this is about when you try to look at an object in the sky. Sorry, I'm just trying to accept at the same time other participants. Yeah, so when you try to look at an object from the sky, could be a star, could be for laser guide stars, kind of a fake star, if you will. So the idea is to look at it, but as the signal goes through the atmosphere, the light goes through the atmosphere, it gets distorted. And when you try to get an image of this object, then it may appear blurry or not in a very good quality. So to change this, you will assess the movement of the atmosphere, the perturbation, and you will correct it with a mirror. So the way the perturbation occurs is at quite high frequency. So you have to go higher than this frequency to be able to correct the signal. So you get an adaptive loop, adaptive optics loop. So as the signal comes through, the mirror will correct, will tilt a little bit, and then the computer will check if this correction is enough or not. And you have this loop that keeps going until you get a very nice image. So this is very often the case for astronomy. Astrophysicists use this technique a lot, but not only. We see more and more examples of people in biophysics using the same principle, but instead of having the atmosphere, you get tissue. And the nice thing about shortwave infrared is that you can penetrate deeper inside the tissue so that you can see things that are at a deeper level. But the idea is the same, right? So instead of correcting the atmosphere perturbation, you will correct the scattering due to the tissue. And usually you have a better resolution and you preserve brightness of the sample. So for adaptive optics, people usually need a sensor that can go very fast. So when you integrate this in a adaptive optics loop, you need to be able to correct this perturbation very fast. So you need a sensor that can have a very high frame rate. This is what our cameras do, especially in the shortwave infrared. We are one of the fastest on the market when it comes to frame rates. And so there are also other things that come with this, with the speed. You need very small latency. So having camera link is a very useful interface because you are able to minimize the latency between the adaptive optics system itself and your camera. So, of course, you get synchronization. If you need to synchronize with a laser pulse, for example, this you can do with our cameras, and you can integrate this in adaptive optics bench setups by having a very nice SDK that supports Python, C, C++, just to name a few. I give you an example. So one of the example, of course, there are customers all around the world, right? But here is one of our customer that is mostly on the OEM side, but it started as a small research project. So what they do now is that they integrate a CRED 3 as a wavefront sensor. On the top right-hand corner, you can see that this is kind of a Shack-Hartmann mounted lens array mounted on the CRED 3, and you have a more complex system where you cannot see the CRED 3, but you would have to believe me that there's a CRED 3 in this system, and the idea is always the same. It's to see objects up in the sky and correct the distortion in a very fast and efficient manner. Of course, this is the example of Imagine Optic. Recently, they got 5 of our CRED 3s because usually they start with 1 or 2, and then if they are happy about it, they go for more. So this is something we see quite often. But there are some research institutes that work with us as well, like the ESO, European Southern Observatory, or KEC. This is, again, just to name a few, but usually what they remember is the speed of the camera. So when they want to have this, when they want to integrate our camera as a wavefront sensor, this is usually the camera they go for. So the second part is about free space optics and telecommunication. To be very straightforward, we talk about lasers. And the first application is laser beam profiling. So as you may know, people used to work in the visible range with laser, but now we are able to to get shortwave infrared lasers, but not only. Some people work also in the UV now. But here, let's focus on the shortwave infrared. Yeah, sorry, I'm just going back. Yeah, so for laser beam profiling, there are two main cameras that may be of interest, CIRED 2 Lite and CIRED 3. These are small cameras, easy to integrate. But usually when people would go for these two cameras, again, they would look at the speed. So laser beam profiling is just to, when you have a laser, to understand different features of this laser. Could be the shape, could be the intensity distribution, the size also. But you need a sensor that is able to work in a fast manner, because the laser deformations may occur in a very small lapse of time. So you need something that go faster to see how it fluctuates. Here is an example of optoscience. I don't know if some guys from optoscience are here, but this is just to show that you can very well assess this fluctuation of a laser in the shortwave infrared. This can be used for additive manufacturing. So you get deposited track. This is the small image on the right, right? So you get a deposited track, and the laser will basically shape this track. And this is how, a bit like printing, but this is more like welding in this case. So you would shape the matter by using a laser and welding on the top of it. This is one of the examples, so it's more towards the industry, but we have some people using it already for this application. So yeah, there are a couple of solutions regarding these applications. So people will usually look at the M square factor. This is basically how nice the laser look like. They would also need something that can go very fast in the shortwave infrared. This is what the CIRED 2 Lite and CIRED 3 do very well. And if you want to trigger, for example, with the laser pulse or with the laser that is a continuous wave, could be both, you can use pulses with the camera, and especially with the CIRED 2 Lite and CIRED 3, you can go down to very small exposure time, even down to a couple of hundreds of nanoseconds. So again, the CIRED 2 Lite at the beginning, just to say it was designed for China because they wanted a camera that has a lower price point, but at the same time, very good technical specificities. So this was like right in the between the between CIRED 3 and CIRED 2. But again, people may use CIRED 3 because if they have enough signal, they don't want to cool the camera. So both are possible, in fact. These are a couple of customers. Not all of them are our customers, but this is just for you to have an idea about potential customers, right? That you could eventually reach out. I'm aware that some of them are in Europe, in the US, but this is more about the applications, right? What these guys work on. And for free space optical communication, again, it has to do with a laser. Here I put CIRED 2 Lite and CIRED 3, but very soon we will talk about CIRED New Space because this fits pretty well in this category as well. So free space optical communication, how does it work? Basically, you have a transmitter and a receiver. You send light with the transmitter, and the receiver will get the signal, and this will be data at the end, right? Very often you see adaptive optics as well that comes before the receiver, just to make sure that the signal comes as you expect it to come, right? The idea behind free space optical communication is that So nowadays things tend to change, but we used to work with radio frequencies, and it has several drawbacks. The drawbacks is that um, if you it's easier to intercept, right? Because the waves are propagating freely in the medium. So anyone that is around is able to catch the signal. When you work with a laser, this is not the case, because if you stop the laser, if you try to intercept the signal, then the communication will be cut and you can see it directly, right? So this is one of the advantage of free space optical communication. The second one is also regarding bandwidth. There is, for example, Blue Origin building systems, and they try to reach 6 terabytes per second, which is huge. And so, yeah, the bandwidth is another advantage of this technique. And people started to work on ground to see basically how it works. But the idea is clearly to go towards space and get this communication between ground and a satellite, for example. And this is how people are doing nowadays. There are different features for this kind of application. For FSO, again, the speed is very important, because when you try to send a signal, so on ground, this will be maybe less a problem. But when you think about a satellite moving very fast, if you want to send a laser from the ground and connect it directly to the sensor in space, then you need a sensor that can react very fast with a high frame rate, so that you can very accurately position the beam. Again, when you talk about speed, you need very low latency, so that's why camera link is interesting. Same goes for the wavelength. In telecommunication, people use 50 nanometers a lot. Some other use 1310 nanometers as well. So these are typical wavelengths that people use in the telecommunication world, but there are some others, of course. And yeah, when we talk about speed, it's all about minimizing the latency, being able to achieve high frame rates, and also the integration, because they have very complex systems, so it needs to be integrated pretty easily. This is another example. There are a couple of them that we already work with. DLR is one of our customers for some time. So when we talk about free space optic or telecommunication, it is very heavily linked to aerospace. So this is why some companies are from this field. Very recently also, I think it was a couple of months ago, we sold 5 Siret 2 lights to Lincoln Laboratory. So this is one of our customers as well, Airbus, as you may know. And this is one of the examples I wanted to show, Miraclass. So this is a company based in France as well. They use a Siret 3 to secure the optical communication. The idea is that they try to provide kind of a forecast of the sky, so that people in the future who would need communication, they would know what would be the best place on Earth to have their system, for example. But the idea is that they want to do even more than that. They want to enable communication, yes, but also look at air pollution, for example, or greenhouse gas emission that you can do from the sky, that you can see from the sky, sorry. So yeah, this was what I wanted to show you, these kind of examples. Next part is quite a big chunk, I would say. It's about quantum sources and nano emitters. There is a part that is more biophysics related, and I wanted to show as well that telecommunication can come into play, because these quantum sources and nano emitters, they can be used for different things. They can be used for imaging, they can be used for telecommunication, and this is what I will show you. So for biophysics, one of the example, this is carbon nanotubes. So here we talk about 2 main cameras, right? Siret 2 and Siret 2 ER, because we deal with very well, rather long exposure time. So you need to cool the sensor to minimize the dark currents. So the carbon nanotubes, this is like a single layer of carbon atoms, and they are rolled up in a tube. And when they are in such shape, they have very specific optical properties, but also electrical and mechanical. And the nice thing about it is that when you excite them, they re-emit in the shortwave infrared. Emitting in the shortwave infrared enables better penetration in the tissue. This is the small diagram or scheme that you can see at the bottom right. With visible light, you are able to penetrate the tissue, but it's only a couple of micrometers usually. With shortwave infrared, you can go down to around 10 millimeters at least. So you are able to go even deeper. And we see people worked in the visible range for decades, and now they are shifting slowly. We see more and more applications, more people using our camera for this application. They move towards the shortwave infrared for this reason. So this is one of the example. Here, they wanted to image inside the brain tissue. So they injected some special carbon nanotubes that are called ultra-short carbon nanotubes, and they will excite them. After exciting them, these carbon nanotubes will re-emit in the shortwave infrared, and you try to see an image with this. Here, I will not talk about QD because this is the topic that is coming right after, but at least this is how shortwave infrared is works pretty well for this kind of application. So the good thing about our camera, especially the C-Red 2, is that you have very low dark current. So if you want to have a good signal to noise ratio, here dark current is a key feature to look at, because as you integrate for longer and longer time, when the exposure time becomes longer, then the dark current will rise. And this is the only way to minimize this is to cool the sensor. So yeah, the C-Red 2 has a very low dark current. We see also in the shortwave infrared, we can go from 900 to 1700, but we see some customers who need to go even further than that, and we can go up to 2.2. So here speed is not really an issue. Here they need a camera that works and operate very well over long exposure times. And this is what the C-Red 2 can do. I just wanted to mention, because it's coming very soon, that some people may be interested in coupling this with a spectrograph to get hyperspectral information. So this is also something they will be able to do. We are aiming for September. So yeah, this is one of the good example I wanted to show. This is, again, someone based in France. He's a key opinion leader in this field. His name is Laurent Cognac. So he is the one who published this paper I showed you, and he designed carbon nanotubes for biophysics and just to be able to image. Again, I'm talking about key opinion leader because he's part of the jury in the ERC, which is one of the biggest council that provides money to research in Europe. And also he published in a couple of high impact factor journals, Nature, Science, to cite a few. Yeah, and some other labs that work. So these guys don't have the C-Red 2, but this is the kind of applications they work on. So these are potential customers. Another kind of nano emitter, these are the nitrogen vacancy centers. Here, people use them in the visible range, but again, they tend to go to the shortwave infrared. Here is a specific application where what they try to do is that they would like to sense the temperature on the sample, and how they do it is that they inject these kind of small nano emitters called nitrogen vacancy diamond centers, color centers, and they have very unique properties, a little bit like the shortwave, like the carbon nanotubes. So when the temperature changes, they will emit light at a specific wavelength. But as I said, when the temperature changes, then this light emitted will shift in terms of wavelength, so that by measuring this shift, they're able to say what was the temperature change. So this is one of the example. We see more people using this kind of nano emitters for thermometry. Here is one of the example, but of course, this is not limited to biophysics. This can go for electronic device when you want to measure accurately temperature shifts, or but also in biology. Yeah, that's also one of the case. Here, I wanted to show you as well that for this example, people were using Nirvana HS. So this is, of course, one of the competitors, but this is just to show that in this field, people need quite a high-end shortwave infrared sensor. And if they use the Nirvana HS, they could be using a C-RAD 2 as well. Of course, they have different features, right? These are not the same cameras, but when you talk about having a low dark current, good signal-to-noise ratio, working at long exposure time, C-RAD 2 could also fit here. So yeah, I will not go through all of them because this is quite repetitive, but the idea is that, yeah, these people want to use the camera at long exposure time, and they need some kind of a nice resolution to see their samples, but also they want to be able to cool down this camera to get a low dark current without using liquid nitrogen. So another nice feature of the C-RAD 2 is that you can only use water to cool it. And usually people prefer this solution because by using water, this is easier than using liquid nitrogen because it needs maintenance, for example. So this is another nice thing with the C-RAD 2. Some examples. To my knowledge, these are not our customers. These are just people I looked at doing this kind of research. But they could be, if there are similar labs in your region, this would be nice to reach out to these people because they may have interest in the C-RAD 2. Again, another kind of nano emitters, still for biophysics. These are the rare earth nanoparticles. Here we talk about nanoparticles usually based on lanthanide, but it could be erbium as well, ytterbium, neodymium, whatever. So these are the atoms they are based on. We also have the rare earth nanoparticles for photothermal therapy. So again, this is quite the beginning, right? People in biophysics start to use it, but there are two reasons for this. So the idea is that they have these nanoparticles made of rare earth. They will excite it with a laser, and they will re-emit in the shortwave infrared. So this is a little bit like the carbon nanotubes case. What they do is that they will be able to image by using this technique, as it was the case for the shortwave, for the carbon nanotubes. But there is also another feature with this kind of nanoparticles. This is that they would generate heat. And when you think about cancer treatment, being able to localize this heat in a very precise manner is important because then you can do tissue ablation in a very localized area. So there are two main features with this kind of nanoparticles is that they can be used for imaging, but they can also be used for treatments. In this paper, they used Nirvana 640 again, but this was to show that they need high-end shortwave infrared cameras. And here again, the C-RED 2 may fit very well. Again, like, of course, this material will be available at the end of the webinar, so you will be able to see it maybe in a more calm environment. But for now, I just wanted to show that the long exposure capability of the C-RED 2 is one of the main features that you need. But when it comes to generating heat, you may need to image at a faster frame rate so that you can control the generated heat over time. And to do this, usually you don't need long exposure time. You work at a higher frame rate. And this is where the C-RED 2 is nice to have because it's versatile. It can work at long exposure time, but also you can operate at faster frame rates. So yeah, this technique is very specific for photothermal therapy because you may need long exposure time, but you can also work at higher frame rate. These are people working on this topic. To my knowledge, we don't have any of these customers yet. But again, this is just to give you a general idea about people that may be interested in the camera. Right, so we talked about biophysics for some time. I will talk about telecommunication now, but still talking about nanoemitters and quantum sources. So this is the last nanoemitter I wanted to show you, quantum dots. So this is the nanoemitter that was also used by Laurent Cognac when he's trying to image through the brain tissue. But here I wanted to show you another example where people use it for telecommunication. So quantum dots, these are small particles made of semiconductor material. And again, they have very specific properties, electrical properties, but more importantly, optical properties. One of them is that when they get excited, they will re-emit light in the shortwave infrared as well. And you can control the wavelength that they re-emit at by tuning their size or their shape. So this is how you can be able to have a broad range of emission in the shortwave infrared. And more importantly, when we talk about telecommunications, we usually talk about O band and C band. And these are the 1310 nanometer wavelengths and 1550. So yeah, here is a bit of a complex setup, but one thing that is nice to note is that for these kind of nanoemitters, they emit light in a very specific manner and in a very efficient way. So people use it because they can re-emit at these specific wavelengths. And so this is not the case for the C-RED 2, right? But usually they would also look at single photons and they need a signal that is very pure. So this is why they would use quantum dots. There may be opportunities with the C-RED 1 since you can do single photon imaging. We didn't get any customers reaching out to us for now, but this is something to keep in mind. Yeah, so this is basically what I wanted to show you. Again, Nirvana is one of the competitors here. They are already in this kind of applications, and the C-RED 2 could also be used here. Yeah, so again, this is kind of the same, right? This is what I said with the C-RED 1. This could be an idea. This could be also coupled with a spectrograph. So this is why when we will release the C-RED 2 for spectroscopy, people may have an interest here, even stronger interest. Also, yeah, synchronization and two specific wavelengths to remember, 1310 and 1550 nanometers. These are potential customers, right? Some industry companies, but also some research labs. The almost last part is about space situational awareness and airborne imaging. I will start with airborne observations, right? So here, most interesting cameras would be CRED 3 and CRED 2 lights. The application is pretty simple. Usually they want to mount this camera on under a plane so that it can look at the Earth, or it could be drones, or it could be even in satellites. Well, this would not be CRED 3 or CRED 2 light in this case, but that would be the CRED new space. And by mounting cameras on drones or planes, you can have different kind of applications. One of the main features of shortwave infrared is that you can better penetrate through the atmosphere. So when you have fog or haze or even smoke, you will be better able to see through this. We have an example of firefighters in France using our camera. They tried it to see in this kind of environment where you have a fire and heavy smokes. So here, shortwave infrared excels, but you can have very diverse applications, right? It could be just for imaging. It could be to monitor greenhouse gases because they have absorption wavelengths in the shortwave infrared, very specific ones. So you're able to localize these gases. But also after a disaster, in some countries, it's very often that you would have earthquakes or fires in the summertime. So this could be used by firefighters, as I said, but not only. At the bottom right hand corner, you can see a drone with a camera where they do hyperspectral imaging, and they would look at how much water you have on the soil, or it could be in the forest as well, because water strongly absorbs in the shortwave infrared. So you are able to detect this just by flying over the forest, for example. So yeah, here the nice features about the CRED series, it's that it can be very small, can be integrated in drones. We already have customers using it for solar panel inspection. So this is another example. But yeah, also you can work in different kind of environments. We know that some people do vibration tests. For us, we don't have them, but our customers usually do it for themselves. And again, you can do imaging during daytime, but also nighttime. So these are the main features. We have one customer in Saudi Arabia that used a CRED 3 for hyperspectral imaging. Basically, he just mounted a CRED 3 on a plane, and he was looking at specific absorption wavelengths to monitor methane and carbon dioxide. But this is not only about this customer, right? We are already working with Thales, L3Harris, Leonardo, and Safran. Safran is based in France as well, mostly for defense. So defense companies may have interest in this kind of cameras as well, because you can see, you can image in different conditions. Could be in a foggy environment, but also during daytime or nighttime. So this is something that they usually look at. Another application is space situational awareness. Here I added the CRED new space, but also CRED 1, because usually they are linked. So situational space awareness is about being able to detect objects coming from the sky. Could be different things, right? So the shortwave infrared here is better than the visible range for same reason as before. It has very high transmission through the atmosphere. You get very low scattering as well, but you can see during daytime satellite. Yeah, and also laser. You can do laser tracking. So on the right side, you can see that, so this is a camera from Raptor, but our cameras could also be used for this. They try to detect satellites in the low Earth orbit. So we talk about an orbit that is rather close to the Earth when you compare it to GEO, for example. So you could detect these satellites by coupling the camera with a telescope. But not only, if you think about further than that, geo orbit, so we are talking about 35,000 kilometers. There are other techniques that exist. The C-RAD one is already used for this. So you can use it for optical interferometry. Basically, you combine signals from different telescopes, and by making the signal interfere, then you are able to localize a satellite that is thousands of kilometers away. So you will not be able to image it, but you will at least know you will be able to localize it. So it has various applications for defense purpose, but also for astrophysicists. So yeah, again, here we talk usually about extremely faint signals. So having a camera with a low dark current is mandatory here. But when you think about space situational awareness, you can think about looking at the sky from the ground, but you can also look from the sky to the ground. So this is where the new space could be used. Yeah, and again, these are kind of the same features here. The speed is usually nice to have because we work with very fast moving objects. So having a high frame rate and very short exposure time is important sometimes. A couple of customers, again, we already work with Boeing, Lockheed Martin. They have C-RAD ones, but I know that we have no one from the US here. But in your region, you may have similar agencies or similar companies working on these problematics. And especially here I talk about shortwave infrared, but it must be said as well that the OCAM that we have in the visible range is used a lot for this kind of purpose. When it comes to space situational awareness, the OCAM is one of our main camera, but this is in the visible range. Now people want to work in the shortwave infrared. And the last application is hyperspectral imaging. So I try to focus this talk on research applications, but when it comes to hyperspectral imaging, usually we are more towards the industry. And here, the fact that you have a camera that can go at very high frame rates is something that would be interesting for the customer, because of course, as you may know, there are several cameras available on the market. They are usually cheaper, but when it comes to going at a high frame rate, we are, I would say, the only one on the market that can go that fast. So this is a differentiator for sure. The hyperspectral imaging is basically about having two information at the same time, the spectral information and the spatial information. So by being able to look at these two things, you will be able to discriminate between different materials or chemicals because they would have different spectrum, reference spectrum. So here at the bottom is an example just to show that using this technique, you can see the difference between two kind of plastics. If you were using visible light, you would not see any difference. If you try to see difference between PP, which is a kind of plastic, or PET, and some others, you will not be able to see the difference with your eye. But if you use this system in the shortwave infrared, you can very nicely see the difference between the two. But this can also be used in the pharma to see the difference between two pills, for example, or food inspection to see potentially if there is a beginning of moisture or water content, for example. So it has diverse applications. For high-speed imaging, usually you need well, for hyperspectral imaging, you usually need the speed. So this is something nice to have, but also you need one of the most important features is that you get nice uniformity over the sensor. And our sensor, the sensors that we integrate, have this feature. And also they have it by default, right? But we, on the top of that, characterize the camera so that we are able to provide an accurate map of the sensor so that people know what to expect in terms of spectral response. So yeah, pixel uniformity is definitely a key thing here. And some potential customers, right? From time to time, we talk to some of them, specking, but they are still in the they are still trying the camera. We don't know yet if they are willing to go forward with this, but at least they try it. They see interest in this camera. And finally, I want to finish with this, is that so we have a GUI, so we have a software, First Light Vision, but we also have an SDK. And when we talk about biophysicists, astrophysicists, or engineers in the physical science, these are people who usually know how to do programming. So using the SDK is very handy for them. We still have a software that can be used, but having this SDK and also the continuous support, our support team helps customers very often when it comes to SDK integration. So I would summarize by saying that, yeah, there are different level of understanding. If you're a beginner, you still have the software to work with, but if you are more advanced in programming, you can go with the SDK. So there are different solutions for different people. And I understand that you may be used to Solus. We are also working on a solution to integrate our cameras in Solus. But for now, for the time being, working with First Light Vision is a way to do it if you don't want to go into programming. And this is all I wanted to show you for this new financial year. If you have any questions, I will gladly listen to you. Just go back here. Right. So I just wanted to say that, well, in the meantime, if you think of anything, please let me know. But this webinar is recorded, so I will give you the link right after this call. I will also send you material. All the slides that I made will be available as well. I will just send you a link with an email just after. And of course, if you have any questions, if you have potential customers interested, or if you have customers with questions that you do not know how to address, feel free to reach out. Right.
Francois, can you hear me? It's Joshua
Yes.
here.
Yep.
Yeah, how you going? We had a recent inquiry for imaging shockwaves for hypersonic applications in a shock tube. Have you done anything like this before, or have any insights in that particular application?
No, we didn't have any customers for this kind of application, but you see, this is interesting to see because we are also looking at this kind of applications, because this is not something we used to do. This is not something that we were really aware of. So having this kind of people coming to us and asking about it is definitely nice to have. So if you have any kind of further information, I saw the emails. I don't remember if I answered them or if it was the service team answering. But yeah.
Yeah, I'm chatting with Sean about it. I mean, because it's a shockwave, obviously, it happens very, very fast, so the frame rate's not an advantage. But I think we have the ability to run CRED2 at sub-microsecond frame rates for a single exposure. So if you could send me any info on that directly, or if you want to put something together for the wider group, that'd be helpful for that particular application.
Yeah. So on this topic, here I showed like the general use of the cameras, but if you think that the camera can be used and if there is a specific thing that we say it's not possible, but that would be a nice opportunity, please let us know, because when we talk about short exposure time, we say that people can use the camera down to 50 microseconds, sometimes 30 for CRED2. But we have customers that use it at even lower short exposure time. We have people using it at 5 microseconds, for example. Of course, it has drawbacks. The camera will not operate as it is the case for 50, but this is something that can be done, and it seems like some people can live with this. They are happy to work at shorter exposure time, even if you get a degraded signal, for example.
Yep. Thank you. Thank you.
You're welcome, and thanks for your question. Right. So if there is no further question, we just stop the recording.
Thank you.
Yeah, thank you everyone for joining. And again,
If
there is any question, feel free to reach out by email or Teams, whatever is more efficient for you.
Thank you.
Thank you very much.
Cheers all. Goodbye.
Bye-bye.